Good day everyone. I am Nandini. Now I am going to talk about the speed control technique of an induction motor. First, let's can see what is meant by an induction motor. An induction motor is an electric motor which usually runs at a speed less than that of a synchronous speed. Hence, it is also known as a synchronous motor. It is not possible for an induction motor to run at a synchronous speed since we know that the slip is equal to ns minus n divided by ns. So here when the rotor tried to run at a synchronous speed, the slip will become 0, which in turn will cause a 0 torque. So it is not possible for an induction motor to run at a synchronous speed. Induction motor mainly consists of a stator and a rotor. The stator is made up of several laminated silicon sheets with the slots which are pressed together to form a stator core. Then the stator slots are occupied by the stator windings. The rotor core is made in the same way as that of a stator core, but here the rotor slots are occupied by conductors instead of winding. The laminations are used in order to minimize the hysteresis loss and the eddy current loss. As shown here, several sheets are pressed together to form a single core for stator and the rotor. Here we can see that the stator slots are occupied by winding and the rotor slots are occupied by aluminium or copper bar. The conductors in the rotor are finally short circuited at both the ends with the help of an end ring. This is the general classification of an induction motor. Depending on the rotor construction, they are classified as squirrel cage induction motor and slip ring induction motor. And depending on the number of phases, they are classified as single phase induction motor and three phase induction motor. Single phase induction motor. It uses a single phase supply for its operation. They are simple in construction and are easy to repair and maintain. Hence, they are economical. But the starting torque here is less when compared to the three phase induction motor. The efficiency is also low since we have only one winding to carry the current. Therefore, since they are economical, they are used in appliances like mixer grinder, fan, and compressors. A disadvantage with the single phase induction motor is that they are not self starting in nature. Therefore, we need to adapt certain method to start this motor. Three phase induction motor. It uses a three phase supply for its operation. Here, the construction is complex and are difficult to repair and maintain. Therefore, they are expensive. But the starting torque is high. The efficiency is also high since three windings are used to carry the current. They are the most common type of motor that are used in the industry. Slip ring induction motor. Here, the rotor slots are parallel in nature, but the construction is complex than that of a squirrel cage induction motor. It has an advantage that we can connect an external resistance to the rotor. By connecting this external resistance, we can have a high starting torque. Therefore, the torque of slip ring induction motor is high than that of a squirrel cage induction motor, but the efficiency is less. It is used in places where high starting torque is required, like hoist, crane, and the elevator. Squirrel cage induction motor. Here, the slots are skewed in nature. The construction is simple, but here the rotor bar are permanently shorted at the end. Therefore, it is not possible to add any external resistance. Therefore, here the starting torque is less and the efficiency is high. It is used in lathe machine, fan and blower. Now let's can see about the working of an induction motor. In three-phase induction motor, the stator winding are displaced by an angle of 120 degree from each other. When the supply is given to the stator winding, a magnetic field is developed around the winding. The magnetic flux developed around each winding will have a phase difference of 120 degree. Due to this change in magnetic flux, an EMF is induced in the rotor. As the rotor is short circuited at both the ends, this EMF will cause a current to flow through the rotor conductor. As we know that when a current carrying conductor is placed in a magnetic field, it will experience a torque. Therefore, the rotor will start to rotate. The rotor rotates and tries to catch the speed of the rotating magnetic field, but it is never possible to attain this speed. It is the basic principle of operation of an induction motor. Speed control method. We can control the speed of an induction motor either from the stator side or from the rotor side. From the stator side, we can control the speed by varying the frequency, by varying the voltage and changing number of poles, V by F control and adding rheostat to the external circuit. From the rotor side, we can control the speed by adding resistance and by cascade control method. Now let's can see about the speed control from the stator side. V by F control. It is the most common type of control that are being used to control the speed of an induction motor. The three-phase induction motor operates in the same way as that of a transformer since they operate on the mutual induction principle. Therefore, the voltage developed is given by V is equal to 4.445 kTf. From this equation, it is clear that the flux phi is directly proportional to voltage and inversely proportional to frequency. Here we can observe that if we decrease the frequency, the flux phi will get increased. The increase in flux will cause the saturation of stator and rotor core. Also, the increase in flux will increase the current through the circuit and will distort the stator flux. Therefore, it is necessary to maintain the flux phi as a constant value. This is achieved by varying the value of voltage proportional to the frequency. Hence, if the frequency is decreased, the value of voltage should be increased, and when frequency is increased, voltage should be decreased. Therefore, here the flux phi is maintained constant. Since we are maintaining the ratio of V by F as a constant, this method is called as a V by F control method. Frequency control. The synchronous speed Ns is equal to 120 F by P, where F is the frequency and P is the number of poles in the stator. When the frequency is decreased, the synchronous speed is decreased, and when frequency is increased, synchronous speed is increased. We know that the rotor always tried to achieve this synchronous speed. So, whenever we change the synchronous speed, the rotor speed, which is given by n is equal to ns into 1 minus s, will also get varied. Therefore, here using this method, we can make the rotor speed above and below the rated speed. Hence, it offers a wide range of speed control. This method is not widely used since changing the frequency is a tedious process. It is used in places where the induction motor is fed from a generator as a prime mover, where this by changing the speed we can easily control the frequency. As we can see here, when the frequency is low, the speed is low but the starting torque is high. As the frequency goes on increasing, the speed gets increased but the starting torque goes on decreasing. From this equation, we can also know that by changing the number of stator poles, we can change the synchronous speed. By changing the poles, it is possible to control the speed above and below the rated speed. This method is used only for a squirrel cage induction motor since the change in poles will not affect the stator. Voltage control. The torque is directly proportional to S into V squared, where S is the slip and V is the stator voltage or the supply voltage that is being given. When the voltage is increased, the torque will get decreased. This becomes a problem when we use a constant load. Therefore, we have to maintain the torque as a constant. In order to achieve this, when the voltage is increased, the value of stator is decreased proportionally in order to maintain the torque as a constant value. Therefore, when the stator voltage is increased, the slip should be decreased, and voltage is increased, slip should be decreased. Therefore, the torque is maintained constant. We know that the voltage is directly proportional to speed. Hence, the voltage is increased means the speed will get increased. This method is not widely used because for changing a small value of speed, we had to vary the voltage to the maximum extent, and decreasing the voltage also increases the current in the motor, resulting in the overheating problem, and the losses of the circuit will also get increased. So this method is not widely used to control the speed. As we can see here, when the value of voltage V1 is high, the torque is high and the speed is also high. When the voltage gets decreased, the speed and torque decreases proportionally. Adding rheostat in the stator circuit. Here, a rheostat is added in the stator circuit. When the value of resistance increases, the voltage at the stator is decreased, which will decrease the torque. Therefore, this method is used to run the motor below the rated speed. Here, we can take fan as an example. In the fan regulator, by changing it, we are varying the rheostat connected to the stator. By keeping it at a maximum value, the resistance added to the circuit becomes zero. Hence, we can have a high speed. When we keep it at a lower value, the resistance added is quite high. Therefore, the voltage is low and hence the speed gets decreased. This method is not widely used since it will result large amount of losses. As we can see, when the voltage is high, the torque is high and the speed is also high. Speed control from the rotor side by adding external resistance on the rotor side. This method is possible only with the slip ring induction motor. Here the torque equation is obtained as tau is directly proportional to S E2 squared R2 by R2 squared plus Sx2 the whole square. We know that an induction motor operates in a low slip region, so Sx2 can be neglected. Also, the voltage E2 is kept constant, so E2 is also neglected. Then we achieve torque tau is directly proportional to SR2 by R2 squared. Hence, on simplification, we get torque tau is proportional to S by R2. Here it is clear that when the resistance R2 increased, the torque gets decreased. So, we are decreasing the value of torque by using this method. As we see that when the value of resistance R1 is very low, then the starting torque is very low and the speed is quite high. When the resistance goes on increasing, the starting torque also increases but the speed decreases. An advantage with this method is that by adding external resistance, we are decreasing the current. When the current decreases, the flux phi also gets decreased. The starting torque tau is directly proportional to cos of the flux. Therefore, the starting torque can be increased by increasing the value of resistance connected to the circuit. Cascade control method. Here, two different motors are used. Both the motors are connected on a common shaft. Hence, they are called as a cascaded motor. One motor acts as a primary and a main motor and another motor acts as an auxiliary motor. Here, the main motor is supplied from a direct three-phase supply and the auxiliary motor is connected to the shaft of the main motor. Therefore, the main motor acts as a supply for the auxiliary motor. When we change the speed of the main motor, the auxiliary motor will also operate depending on the main motor. Here, by using this method, four values of speed control is possible. Let P1 be the number of pole in the main motor and P2 be the number of pole in the auxiliary motor. Therefore, when the auxiliary motor is off, the speed will be S is equal to 120 F by P1. When the main motor is off, then the auxiliary motor synchronous speed will be 120 F by P2. When both the motors are operating and the torque developed in both the motors are in the same direction, then it is called as a cumulative speed control and the value of speed is given as 120 F by P1 plus P2. When the torque developed in both the motors are in the opposite direction, it is called as a differential speed and it is given by 120 F by P1 minus P2. These are the overview of a speed control method available in an induction motor. Thank you.